3 fireballs in 11 days. Same trajectory, same terminal altitude, same geographic corridor stretching from the Pacific Northwest down through the central United States to the Gulf Coast. And the people whose job it is to explain things like this to the rest of the scientific community are not, at the moment, explaining it. Not because they do not have theories, they have several. Not because the data is insufficient. The data is extensive, cross-referenced across multiple independent detection networks, verified by radar, by infrasound arrays, by the all-sky camera systems that have been watching the American night sky continuously for years. The data is good. The problem is that the data is saying something that none of the existing theories, in their current form, fully accommodates. And in the specific community of researchers who study the interaction between the Earth and the debris that the solar system delivers to it on a continuous basis, the gap between what the data says and what the theories predict is the kind of gap that generates the particular quiet that precedes a significant revision in understanding. A fireball is a meteor bright enough to be seen in daylight or to cast visible shadows at night. The technical threshold is apparent magnitude -4, roughly the brightness of Venus at its most brilliant, though in practice the events that generate scientific attention tend to be significantly brighter than that threshold. Every year, thousands of fireballs occur over the United States alone. Most of them are random, unrelated events, the product of the constant rain of interplanetary debris that the Earth sweeps up as it travels through the solar system at approximately 30 kilometers per second. The debris ranges in size from dust grains that produce the faint streaks visible on any clear night, to meter-sized boulders that produce brilliant fireballs visible across multiple states, to the rare, multi-meter objects that produce the kind of terminal airbursts that release energy equivalent to nuclear weapons, and that are recorded on the infrasound networks originally built to monitor nuclear testing. What makes a pattern within that constant rain significant? What justifies the attention that the current pattern is receiving from the researchers monitoring it is not simply the occurrence of multiple fireballs within a short time period. Multiple fireballs within a short time period occur regularly and are expected statistically as a consequence of the Earth's passage through meteor streams, concentrations of debris left along the orbital paths of comets and asteroids that the Earth crosses at predictable times each year. The annual meteor showers, the Perseids of August, the Leonids of November, the Geminids of December, are exactly this phenomenon, the Earth passing through a debris stream and sweeping up an elevated number of particles that produce an elevated rate of meteors visible from the surface. Meteor showers are expected. Their trajectories are known in advance because they come from a specific direction in the sky, the radiant point from which all the meteors of a given shower appear to originate, which reflects the geometry of the Earth's passage through the debris stream. The current pattern is not a meteor shower. The 3 fireballs that initiated the scientific attention are not converging on a common radiant point in the way that meteor shower meteors do. Their trajectories, when reconstructed from the camera and radar data, are consistent with objects approaching from different directions in the sky, which is the signature of a sporadic meteor background rather than a stream. Sporadic meteors, those not associated with any known stream or shower, are the debris of the solar system that has been dynamically dispersed from its original orbital concentration by gravitational interactions with the planets and by the non-gravitational forces that act on small bodies in the solar system, and that now fills interplanetary space in a relatively uniform background population. The Earth samples this sporadic background continuously, and the fireballs it produces appear from random directions at random times with a rate that reflects the density of the sporadic population in the Earth's current orbital neighbourhood. The current pattern differs from the expected sporadic background in ways that the researchers analysing it are still working to characterise precisely, but that have been sufficient to distinguish it from normal statistical fluctuation with a confidence that motivated the analysis that is now underway. The first distinguishing feature is the terminal altitude of the events. All 3 fireballs in the 11-day sequence terminated, meaning they ceased to produce visible luminosity, at altitudes between 38 and 42 kilometers above the surface. Terminal altitude is determined by the size, composition, density, and entry angle of the incoming object, and by the atmospheric density profile along its path. For a given entry velocity and angle, Objects of similar composition tend to terminate at similar altitudes because they deposit most of their kinetic energy in the atmosphere at the altitude where the atmospheric ram pressure equals the mechanical strength of the object, causing it to fragment and rapidly decelerate. The clustering of three unrelated sporadic fireballs within a narrow terminal altitude range over an 11-day period is statistically unusual. The second distinguishing feature is the geographic corridor. The terminal points of the three events, the locations on the ground directly below where the visible luminosity ceased, fall within a corridor approximately 800 kilometers wide, oriented roughly north-south along the western half of the North American continent. The probability of three random sporadic fireballs terminating within a corridor of this width over an 11-day period is low enough to merit investigation, but not so low as to be immediately diagnostic of a non-random cause. The significance of the corridor clustering depends on the details of the calculation, on the assumptions made about the background sporadic rate and its geographic uniformity, and on the specific hypothesis being tested. The researchers conducting the analysis have been careful not to claim statistical significance before the calculation has been completed, with the appropriate rigor and the appropriate accounting for the multiple comparison problem that arises when looking for patterns in a dataset after the patterns have already been noticed. The multiple comparison problem is a statistical pitfall that is particularly relevant to the search for patterns in meteor data. If you examine enough different potential pattern signatures in a dataset, the probability of finding at least one apparent pattern by chance, even in data that is actually random, becomes high. The human visual and cognitive system is extremely good at finding patterns, including patterns that are not real, because the ability to detect patterns in environmental data was strongly favoured by natural selection in circumstances where false positives, seeing a pattern that was not there, were much less costly than false negatives, missing a pattern that was really there. The result is a cognitive architecture that is systematically prone to over-detecting patterns, particularly in sparse and noisy data. The researchers analysing the current fireball pattern are aware of this and are applying appropriate statistical methods to test whether the pattern survives correction for the multiple comparison problem. The infrasound data from the three events is the most technically detailed and scientifically rich dataset available for characterizing the physical properties of the incoming objects. Infrasound, acoustic waves at frequencies below the threshold of human hearing, is produced by fireballs through two mechanisms. The first is the direct acoustic radiation from the shockwave generated by the supersonic passage of the meteoroid through the atmosphere, a continuous source that produces infrasound along the entire luminous trajectory. The second is the impulsive acoustic signal from the terminal fragmentation event, when the meteoroid breaks apart and rapidly decelerates, producing a pressure pulse that propagates outward from the fragmentation point and can be detected by infrasound arrays at distances of thousands of kilometers. The Comprehensive Nuclear Test Ban Treaty Organization's International Monitoring System Infrasound Network, which operates a global array of infrasound stations for the detection of nuclear explosions, also detects fireball infrasound routinely and provides the most sensitive and geographically comprehensive infrasound monitoring available. The infrasound signals from the three fireballs in the current pattern have been analysed by the groups with access to the IMS data, and the analysis has produced yield estimates of the total energy released by each event in the atmosphere, that are consistent with objects in the size range of approximately 0.5 meter to 1.5 meters in diameter, depending on the assumed bulk density and entry velocity. Objects in this size range are too small to survive intact passage through the atmosphere and too small to be detected by any current telescopic survey before their arrival. The asteroid and comet survey programs that monitor the near-Earth object population are highly effective at detecting objects larger than approximately 10 meters and have catalogued more than 90% of the near-Earth objects larger than 1 kilometer. For objects below approximately 1 meter, the survey programs have no practical detection capability, and the Earth's interaction with this size population is only characterized through the statistical analysis of the fireball record itself. The fireball record maintained by NASA's Center for Near-Earth Objects Studies and by the network of all-sky cameras operated by the American Meteor Society, by the Global Meteor Network, and by various national and university programs, provides the database from which the statistical properties of the sub-meter near-Earth object population are inferred. The rate of fireball events of a given energy yield follows a power law distribution, with lower energy events being more common than higher energy events by an amount that is reasonably well characterized by the data accumulated over decades of monitoring. The current pattern of 3 events in 11 days, each in the energy range characteristic of half-meter to meter-sized objects, is being evaluated against this power law background rate to determine whether the clustering represents a statistically significant departure from the expected random distribution. The all-sky camera networks that provide the primary optical data on fireball events have expanded dramatically in capability and coverage in the past decade. The Global Meteor Network, a collaborative project involving camera operators in dozens of countries, now operates more than 1,000 cameras distributed across Europe, North America, Australia, and other regions, providing nearly continuous coverage of the night sky over much of the populated world. Each camera captures video at high frame rates and wide field of view, automatically detecting and recording meteor events and transmitting the data to central processing servers, where the events are characterized in terms of their trajectories, velocities, and luminosities. The simultaneous detection of a fireball by multiple cameras at different locations allows the triangulation of the trajectory in 3 dimensions and the calculation of the pre-atmospheric orbit of the incoming object, the orbit it was following in interplanetary space before it encountered the Earth's atmosphere. The pre-atmospheric orbits of the 3 fireballs in the current pattern have been calculated from the multi-station camera data, and the orbital elements that characterize those orbits are one of the key pieces of information being used to assess whether the events could share a common origin. Objects that share a common origin, whether they were produced by the fragmentation of a larger parent body or are concentrated in a stream that the Earth is currently passing through, will have similar orbital elements because they were released from a parent orbit with velocities that were small compared to the orbital velocity, and therefore diverged only slowly from the parent orbit over time. The degree of similarity in orbital elements required to infer a common origin depends on how much time has elapsed since the objects separated from their parent, because orbital elements evolve over time due to gravitational perturbations by the planets and due to the non-gravitational forces that act on small bodies. The orbital elements of the 3 fireballs, while showing some degree of similarity, are not sufficiently similar in the preliminary analysis to conclusively establish a common origin through orbital comparison alone. The similarity is greater than would be expected by chance for randomly selected sporadic orbits, but the statistical significance of the similarity is not yet at the level that would constitute a confident identification. This is the kind of marginal result that is scientifically most interesting, because it is ambiguous enough to require additional data and more sophisticated analysis to resolve, and because the resolution of the ambiguity will either confirm a common origin, with implications for the near-Earth object population that will require explanation, or rule out a common origin and leave the statistical clustering in terminal altitude and geographic corridor as a coincidence that the statistics allowed. The possibility of a common origin for the 3 events, if it were confirmed, would raise questions about the nature of the parent body and the mechanism by which it produced the 3 objects that struck the Earth within 11 days of each other. The scenario in which a larger object fragments in interplanetary space and the fragments arrive at the Earth on closely spaced trajectories has precedent in the observational record. The Chelyabinsk event of February 2013, the most energetic fireball recorded in the instrumental era, occurred on the same day as the close approach of asteroid 2012 DA14, a coincidence that was analysed carefully by the meteor science community and concluded to be exactly that, a coincidence, with no physical connection between the 2 events established. The simultaneous occurrence of 2 large meteor events on the same day was a reminder that the background rate of large fireball events is high enough that coincidences of timing are not as improbable as they might intuitively seem. The Chelyabinsk event itself was a scientific landmark whose aftermath is still being studied. The superbolide, as fireballs of extraordinary brightness are technically classified, entered the atmosphere over the Ural Mountains of Russia on the morning of February 15, 2013, moving at approximately 19 kilometers per second at an angle of approximately 18 degrees to the horizontal. The shallow entry angle meant that the meteoroid traversed a long path through the atmosphere, depositing its energy over a wide area rather than concentrating it at a single point. The total energy released was approximately 400 to 500 kilotons of TNT equivalent, roughly 30 times the energy of the Hiroshima atomic bomb, making it the most energetic fireball event since the Tunguska event of 1908. The terminal fragmentation occurred at an altitude of approximately 23 kilometers above the Chelyabinsk region, producing a pressure wave that propagated outward and broke windows in buildings across an area of several thousand square kilometers, injuring more than 1,500 people, primarily from broken glass. The infrasound signal from the event was detected by every station in the IMS network and propagated around the globe multiple times, providing a dataset of extraordinary scientific value for the characterization of large fireball infrasound signatures. The Chelyabinsk meteoroid was approximately 17 to 20 meters in diameter before it entered the atmosphere, placing it in the size range that current telescopic surveys have very limited ability to detect before Earth encounter. At the time of its entry, no asteroid of this size had been detected in the vicinity of the Earth in the preceding months, and the approach of the Chelyabinsk meteoroid was entirely undetected. This was not a failure of the survey programs operating at the time. It was a reflection of the fundamental limitation that objects of this size are simply too small and too faint to be reliably detected by current survey technology at the distances required to provide meaningful warning time. The Chelyabinsk event demonstrated that the near-Earth object hazard extends well below the 10-meter threshold that the survey programs have been focused on, and that the intermediate size range between 1 and 20 meters represents a significant, uncharacterized hazard that produces events capable of causing widespread property damage and injury, even though they are not large enough to cause civilization-threatening consequences. The three fireballs in the current pattern are smaller than Chelyabinsk, in the half-meter to meter-and-a-half range based on the infrasound yield estimates, and therefore represent a lower energy category that would not produce the kind of widespread damage that Chelyabinsk did. Objects in this size range typically deposit most of their kinetic energy high in the atmosphere, at the terminal altitudes of 38 to 42 kilometers that characterize the current events, and the energy that reaches the surface as an acoustic shockwave or as surviving meteorite fragments is a small fraction of the total entry kinetic energy. The concern about the current pattern is therefore not primarily about the immediate hazard from the three events themselves, which was limited to a brief period of extraordinary aerial luminosity and a mild infrasound pulse that was recorded by the monitoring network but not widely felt at the surface. The concern is about what the pattern might indicate about the near-Earth object environment that the Earth is currently moving through, and whether that environment contains larger objects that have not yet encountered the Earth, but that might, if the clustering is real and its cause is understood, be predicted to do so. This is the consideration that gives the pattern its scientific urgency beyond the intrinsic interest of the events themselves. If the three fireballs are not random, sporadic events, but represent the Earth's sampling of a concentration of objects in a particular region of interplanetary space, then the concentration may include objects larger than the ones that have already struck, objects that the current survey telescopes have not yet detected, objects whose existence and orbital properties are being inferred from the fireball pattern rather than from direct telescopic observation. The inference of larger companion objects from the properties of smaller detected objects is a standard technique in solar system science. The size-frequency distribution of objects in any dynamically associated population follows predictable statistical patterns, and the detection of objects at the small end of the distribution allows inference of the number of objects at larger sizes with calculable uncertainty. If the fireball pattern is consistent with the Earth's passage through a debris cloud produced by the recent fragmentation of a larger parent body, the size-frequency distribution of the cloud can be estimated from the properties of the detected events, and the existence of larger, undetected fragments can be inferred statistically. The recent fragmentation scenario is one of the hypotheses being actively evaluated by the research teams analysing the current pattern. The fragmentation of small asteroids in the near-Earth object population is a known process that has been studied extensively in the context of both observational evidence and laboratory experiments on the fragmentation of rocky and metallic materials under impact loading. Small asteroids in the near-Earth population are subject to the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, known as the Yorp effect, which is a non-gravitational torque produced by the asymmetric re-emission of absorbed solar radiation from an irregularly shaped rotating body. The Yorp effect can, over timescales of millions of years, accelerate the rotation of a small asteroid to the point where centrifugal forces overcome the internal cohesion of the body, and the asteroid begins to shed material from its equatorial region or fragments entirely. The fragments produced by Yorp-driven spin-up fragmentation would be released with velocities that are small compared to the parent body's orbital velocity, and would initially travel in orbits very similar to the parent's orbit, before slowly diverging over time due to gravitational perturbations. A fragmentation event that occurred years to decades before the current fireball pattern would have produced a debris cloud that has had time to spread along the parent orbit, but that has not yet dispersed enough to eliminate the concentration of objects along the orbital path. The Earth's intersection with this orbital path, if the parent orbit crosses the Earth's orbit at the right time, would produce an elevated rate of fireball events from a particular direction in the sky, a new, undocumented meteor stream. The detection of such a stream from the fireball data would require the orbital elements of the three detected events to converge on a common radiant point and to be consistent with objects on orbits that intersect the Earth's orbit at the current time. The preliminary orbital analysis is not conclusive on this question, which is why the research teams are being careful about their public statements, and why the scientific community is watching the analysis with a combination of interest and caution. The caution is warranted by the history of claimed meteor stream associations that did not survive rigorous statistical testing. The meteor science literature contains numerous examples of proposed new streams that were identified from small samples of events and that were subsequently shown to be consistent with random sporadic background when tested against the full dataset with appropriate statistical methods. The human tendency to see patterns in random data is as relevant to trained scientists as to the general public, and the history of meteor science has been shaped by the effort to develop rigorous methods for distinguishing real stream associations from chance clustering in the sporadic background. The methods that have been developed, involving careful comparison of orbital similarity statistics against the distribution expected from random sporadic orbits, are applied routinely to new proposed associations and frequently result in the rejection of claimed streams that do not meet the significance threshold. The current pattern is being subjected to exactly this analysis, and the results will be published in the peer-reviewed literature, where they will be scrutinized by the broader community before the claim of a real pattern, if that is what the analysis supports, is accepted. The publication timeline for this kind of analysis is typically weeks to months, depending on the speed of the analysis and the peer review process. In the meantime, the monitoring networks are continuing to operate and the data continues to accumulate. If the pattern is real, additional events in the same corridor and with similar terminal altitudes should occur over the coming weeks and months, providing additional data points that will either strengthen or weaken the statistical case for the pattern. The monitoring network is the tool that will resolve the question, which is both the strength and the limitation of observational science. The answer is in the data. The data takes time to accumulate. The accumulation is continuous and automatic, happening whether anyone is watching or not, adding to the archive that future analysis will draw on. The American Meteor Society's Fireball reporting system, which allows members of the public to submit reports of fireball sightings through a web interface or mobile application, has been receiving an elevated number of reports from the western and central United States over the period corresponding to the scientific detection of the current pattern. Public fireball reports are an important supplement to the instrumental network data because they provide geographic coverage that the camera network does not uniformly achieve, and because they capture the visual appearance, sound, and duration of events as experienced by observers at the surface, information that complements the instrumental measurements in characterizing the events. The elevated public reporting rate over the current period is consistent with the instrumental detections, but does not add independent statistical weight to the pattern claim, because the public reporting rate is influenced by factors other than the actual fireball rate, including weather, population density, and the varying attention that people pay to the night sky, depending on their activities and circumstances. The weather factor is particularly relevant to the geographic corridor of the current pattern. The western and central United States in the current season are characterized by the kind of clear night skies that maximize the visibility of fireball events from the surface. Clear skies increase both the rate of instrumental detection by the all-sky camera network and the rate of public sightings because clouds obscure fireballs regardless of how bright they are. The elevated fireball reporting from the corridor must therefore be interpreted in the context of the favorable observing conditions that have prevailed in the region, and the statistical analysis must account for the observing efficiency as a function of cloud cover to properly assess whether the detected event rate is genuinely elevated above the background, or whether it reflects improved detection efficiency due to better weather. The radar data from the Operational Weather Radar Network, the WSR-88D NEXRAD system, that covers most of the continental United States, provides an additional independent dataset that is relevant to the characterization of the fireball events. Large fireballs produce ionized trails in the upper atmosphere that can be detected by weather radar as anomalous returns at altitudes well above the weather systems that the radar is designed to monitor. The radar detection of meteor trails is a well-established phenomenon that has been used in the meteor science community to characterize events whose optical detection was obscured by clouds, and to provide independent trajectory information for events where the camera network triangulation is uncertain. The NEXRAD data from the periods of the 3 current events is being analysed by the groups with access to the Operational Radar Archive, which requires coordination with the National Weather Service because the Radar Data Archive is not routinely accessible to the research community in a form suitable for meteor science analysis. The coordination between the meteor science community and the National Weather Service over access to the NEXRAD archive is a microcosm of the broader challenge of conducting meteor science research with data that was collected for operational purposes by agencies that do not have meteor research as a primary mission. The IMS Infrasound network was built for nuclear test monitoring. The NEXRAD network was built for weather monitoring. The all-sky camera networks were built by the meteor science community specifically for meteor research, but rely on volunteer operators and university-maintained infrastructure rather than on operational government programs. The integration of data from these diverse sources, each with different data formats, different data access protocols, and different temporal and spatial coverages, is a significant practical challenge that the research teams working on the current pattern are navigating simultaneously with the scientific analysis. The Jet Propulsion Laboratory's Centre for Near-Earth Object Studies maintains the most comprehensive database of known near-Earth objects and provides the authoritative assessments of the impact probability of specific objects on specific future dates. The Sentry Impact Monitoring System, operated by CNEOS, automatically calculates the impact probability of newly discovered near-Earth objects and updates the calculations as new observations are incorporated. The current fireball pattern does not correspond to any known object in the Sentry database because the objects producing the fireballs were not detected before their atmospheric entry and therefore were never in the database. The pattern is relevant to CNEOS's broader mission of characterizing the near-Earth object population, not because it involves a specific identified threatening object, but because it is providing new information about the density and distribution of sub-meter to meter-sized objects in the near-Earth environment that can be used to refine the statistical models of the impact hazard at this size range. The statistical models of the near-Earth object impact hazard are expressed as impact frequencies as a function of impact to size, typically presented as the expected number of impacts per year globally for objects larger than a given diameter. The models are derived from a combination of telescopic survey data for larger objects, fireball data for sub-meter to meter-sized objects, crater counts on the Moon and other airless bodies for calibration, and dynamical models of the delivery of material from the main asteroid belt and from cometary populations into near-Earth orbits. The current fireball pattern, if it represents a genuine statistical elevation in the impact rate for objects in the half-meter to meter size range, would constitute new data that modifies the frequency estimate at that size. Whether the modification is significant in absolute terms depends on the magnitude of the elevation and on the duration over which it persists, which are both quantities that the ongoing analysis is working to determine. The Tunguska event of June 30, 1908 remains the most significant, well-documented large fireball event in the historical record, and provides a reference point for discussions of the impact hazard from objects in the 10 to 100 metre size range. The Tunguska event was an airburst at approximately 5 to 10 kilometres altitude over a remote region of Siberia that produced a blast wave equivalent to 10 to 15 megatons of TNT, flattening approximately 2,000 square kilometres of forest. No impact crater was formed because the object disrupted entirely in the atmosphere before reaching the surface. The cause of the event was debated for decades, with proposed explanations ranging from a small comet to a stony asteroid, but the current scientific consensus, based on the analysis of small silicate spherules recovered from the peat bogs of the region and on the dynamical modelling of the event, is that the Tunguska impactor was a stony asteroid, approximately 50 to 80 metres in diameter. An object of this size approaching the Earth today would be too small to be reliably detected by current survey programs before its arrival, and the warning time, if it were detected at all, might be measured in hours rather than days or weeks. The lesson of Tunguska for the current fireball pattern is not that the pattern is indicative of an imminent Tunguska-scale event. The current events are too small by several orders of magnitude in energy to represent objects anywhere near the Tunguska size range. The lesson is about the relationship between the detectable and the undetectable in the near-Earth object population, and about the value of the fireball monitoring network as a tool for characterizing portions of the size distribution that telescopic surveys cannot reach. The current pattern, whatever its ultimate explanation, is adding data about the sub-meter to meter size range that improves the understanding of the near-Earth object environment at sizes that are too small for telescopic survey, but that contribute to the overall statistical characterization of the hazard. The planetary defense community, the collection of scientists, engineers, and policy experts who study the assessment and mitigation of the near-Earth object impact hazard, has been expanding its activities and its institutional presence over the past decade in response to both the scientific developments, including the Chelyabinsk event, and the growing recognition by governments and international organizations that the impact hazard is a genuine risk that deserves systematic attention. The establishment of NASA's Planetary Defense Coordination Office in 2016, the development of international coordination frameworks through the United Nations Committee on the Peaceful Uses of Outer Space, and the execution of the first planetary defense mission, the Double Asteroid Redirection Test, or DART mission, which successfully changed the orbit of the asteroid Dimorphos by impacting it at high speed in September 2022, all represent milestones in the institutionalization of planetary defense as a scientific and policy priority. The DART mission was a demonstration of the kinetic impactor technique for changing the orbit of an asteroid that poses an impact threat. The spacecraft, roughly the size of a vending machine, was launched in November 2021 and impacted Dimorphos, a small moon of the near-Earth asteroid Didymos, at approximately 6.1 kilometers per second on September 26, 2022. The impact changed the orbital period of Dimorphos around Didymos by 33 minutes, a change significantly larger than the minimum required to demonstrate mission success, reflecting the contribution of the ejector plume produced by the impact to the momentum transfer, in addition to the direct momentum of the spacecraft itself. The success of DART demonstrated that the kinetic impactor technique is viable for deflecting small asteroids, and provided a foundation for the development of planetary defense mission concepts for larger and more threatening objects. The applicability of the kinetic impactor technique to objects in the size range being discussed in connection with the current fireball pattern is straightforward in principle. Objects in the half-meter to meter size range are so small that even a modest spacecraft impact would impart a velocity change sufficient to deflect them significantly over a period of months. The practical challenge is detection. An object in this size range cannot be detected by current survey programs at the distances required to provide the months of warning time needed to plan, launch, and execute a deflection mission. The current fireball pattern is being studied partly as an indicator of what kinds of objects might be lurking in the near-Earth environment that the survey programs cannot see, and the development of improved survey capabilities for smaller objects is a long-term goal of the planetary defense community that the current pattern adds scientific motivation to pursue. The proposed next generation of planetary defense survey systems including the Near-Earth Object Surveyor Space Telescope that NASA has been developing for launch in the late 2020s, is designed to significantly improve the completeness of the Near-Earth Object Catalogue for objects larger than approximately 140 meters, the size threshold at which impacts are capable of causing regional-scale damage. The surveyor's infrared detection capability will find asteroids that are dark and difficult to detect in visible light, which represents a significant incompleteness in the current catalogue. For objects smaller than 140 meters, including the size range of the current fireball pattern, the surveyor will provide some improvement in detection completeness, but will not achieve the comprehensive coverage that would make this size range as well characterized as the larger size ranges. The characterization of the sub-100 meter near-Earth object population remains a challenge that the current generation of planned survey systems will only partially address. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, began its full survey operations in the mid-2020s and is producing a new generation of near-Earth object detections at the faint end of the magnitude distribution accessible to ground-based telescopes. The Rubin Observatory systematically surveys the sky to a depth that will detect near-Earth objects significantly smaller than previous ground-based surveys could routinely find, and it is expected to increase the known near-Earth object catalogue by hundreds of thousands of objects over its 10-year survey lifetime. The new detections from Rubin include objects in the 20 to 100 meter size range that previous surveys largely missed, and the orbital and physical characterization of these newly detected objects is expanding the understanding of the near-Earth object population in the size range most relevant to the Tunguska-class impact hazard. The connection between the Rubin Observatory detections and the current fireball pattern is indirect, but potentially important. If the current pattern reflects the Earth's passage through a debris cloud produced by the recent fragmentation of a parent object, the parent object or its largest surviving fragments might be detectable by Rubin if they are in the size range that Rubin can observe. A search of the Rubin data for objects on orbits consistent with the fireball trajectories is a straightforward extension of the ongoing analysis and is being coordinated by the groups with access to both the fireball data and the Rubin data products. The identification of a parent object in the Rubin catalogue would be a significant result that would both explain the current pattern and provide direct observational evidence of a fragmentation event in the near-Earth object population, which would have implications for the understanding of the physical processes that produce debris in the near-Earth environment. The physical processes that produce debris in the near-Earth environment are diverse and not fully understood. In addition to the YORP-driven spin-up fragmentation described earlier, near-Earth objects can fragment through tidal disruption during close planetary encounters, through thermal fracturing driven by the diurnal temperature cycle on their surfaces, through collisions with other objects in the near-Earth population, and through the volatile-driven activity that is associated with cometary objects as they approach the Sun and their surface ices sublimate. The distinction between asteroidal and cometary objects in the near-Earth population is not as sharp as the classical taxonomy suggests, because some objects that have the orbital characteristics of asteroids show cometary activity when observed with sufficient sensitivity, and the material properties of many near-Earth objects are consistent with a cometary origin, even if the objects are not currently active. The physical diversity of the near-Earth object population means that the debris-producing processes operating on it are also diverse, and the characterization of a specific debris-producing event, like the potential fragmentation implied by the current fireball pattern, requires information about the parent body's physical properties that may not be available if the parent has not been directly observed. The spectroscopic characterization of near-Earth objects, which provides information about the mineralogy of their surfaces and thereby constrains their bulk composition and likely origin, has been advancing rapidly as observational facilities and analysis techniques have improved. Spectroscopic surveys of near-Earth objects have revealed a diverse population that includes representatives of most of the major compositional classes found in the main asteroid belt, as well as objects whose spectral properties are consistent with a cometary origin. The surface mineralogy of an asteroid determines its thermal and mechanical properties, including its strength against fragmentation, its thermal inertia, and its YORP efficiency. Objects with low strength, like rubble pile asteroids, held together primarily by gravitational attraction rather than by material cohesion, are more susceptible to warp-driven spin-up fragmentation than monolithic objects with high material strength. The near-Earth population contains a significant fraction of rubble pile objects, as demonstrated by the results of the Hayabusa and Hayabusa 2 sample return missions to the asteroids Itokawa and Ryugu, respectively, both of which were found to be highly porous rubble piles with very low bulk densities and negligible material cohesion on scales larger than individual boulder sizes. A rubble pile near-Earth object undergoing warp-driven spin-up would shed material from its surface as centrifugal acceleration approaches the gravitational acceleration at the equatorial surface, producing a stream of small debris objects released with velocities that are small compared to the parent's orbital velocity, but that are sufficient to disperse the debris along the parent orbit over timescales of years to decades. If the parent was subsequently deflected by a planetary encounter or perturbed by the Yarkovsky effect into an orbit that intersects the Earth's orbit at the current time, the Earth would sweep through the debris stream and produce an elevated rate of fireball events from the direction of the parent orbit's radiant. The current fireball pattern is consistent with this scenario in a general sense, though the specifics of the orbital geometry and the parent body's physical properties would need to be worked out in detail to assess whether the scenario is quantitatively consistent with the observations. The Yarkovsky effect, which drives the slow drift of near-Earth object orbits over timescales of millions of years due to the asymmetric re-emission of absorbed solar radiation, is the primary mechanism by which material from the main asteroid belt is delivered to near-Earth orbits and by which near-Earth objects are eventually removed from near-Earth orbits by planetary encounter or solar approach. The Yarkovsky drift rate depends on the object's size, thermal properties, rotation rate, and obliquity, and varies significantly across the near-Earth population. For objects in the half-meter to meter size range relevant to the current fireball pattern, the Yarkovsky drift rate is high enough to produce significant orbital evolution over timescales of thousands of years, meaning that the current orbital configuration of a potential debris cloud would differ significantly from the configuration at the time of the fragmentation event. The reconstruction of the pre-fragmentation orbital history from the current fireball data requires a dynamical model that accounts for the Yarkovsky evolution of the debris orbits over the relevant timescale, which is a computationally intensive calculation that is being set up by the dynamical astronomy groups engaged with the analysis. The light curves of the three fireballs, the variation in brightness over time as the meteoroids traverse the atmosphere, provide additional constraints on the physical properties of the objects that complement the infrasound yield estimates and the orbital calculations. The light curve of a fireball reflects the rate at which kinetic energy is deposited in the atmosphere, which in turn depends on the rate of mass loss from the meteoroid surface through ablation, and on the rate of catastrophic fragmentation events that produce sudden increases in the effective cross-sectional area and therefore in the ablation rate. A fireball with a smooth, gradually brightening light curve, followed by a single terminal flare, is consistent with a relatively strong, coherent object that ablates progressively and fragments catastrophically at a single altitude. A fireball with an irregular light curve featuring multiple brightness peaks is consistent with a more fragile object that undergoes multiple partial fragmentation events as it descends through the increasingly dense lower atmosphere. The light curves of the three current events, as extracted from the all-sky camera data, show a pattern that is more consistent with the second category, with multiple brightness peaks suggesting fragile objects that fragment progressively during atmospheric entry, rather than surviving to a single terminal fragmentation event. This morphology is consistent with objects of cometary or highly porous asteroidal composition, which tend to have lower bulk densities and lower mechanical strengths than compact stony or metallic asteroidal objects. The light curve morphology is not definitive on its own because the interpretation of fireball light curves in terms of physical properties involves significant modelling assumptions about the ablation and fragmentation processes that are not precisely calibrated. But it adds to the growing picture that the current events may involve material with physical properties that differ from the typical sporadic fireball background, which is dominated by debris from the main asteroid belt, with compositions that span the range from relatively strong stony material to very fragile carbonaceous material. The fragility of the objects implied by the light curve morphology, if combined with the orbital data to place them in a compositional context, might help to identify the population from which they originate. Cometary debris is typically more fragile than asteroidal debris because cometary nuclei are composed of ices mixed with silicate and organic material in a loosely consolidated structure that is mechanically weak compared to the solid rock of stony asteroids. When cometary debris enters the atmosphere at high velocity, it tends to fragment early and deposit its energy high in the atmosphere, which is consistent with the terminal altitudes of 38 to 42 kilometers observed in the current pattern. The terminal altitude is one of the primary discriminants between different compositional classes of meteoric material, with fragile cometary debris terminating at higher altitudes than stronger, stony material of equivalent size and entry velocity. The identification of the current fireball events as potentially cometary in origin would place them in a context that connects the pattern to the broader dynamics of the solar system in a way that the sporadic asteroidal background does not. Cometary material in the near-Earth environment originates primarily from short-period comets, comets with orbital periods less than 200 years that have been captured from the outer solar system into orbits that bring them repeatedly close to the Sun and to the inner planets. The Halley-type and Jupiter family comets that represent the primary reservoir of short-period cometary material undergo progressive physical evolution during each perihelion passage, losing mass through sublimation of surface ices and ejecting dust and debris that populates the cometary debris streams responsible for the annual meteor showers. As comets are depleted of their surface volatiles through repeated perihelion passages, they eventually cease to be active and leave behind a nucleus of refractory material that may be either a dead comet nucleus or a gravitationally bound rubble pile of debris. The near-Earth object population includes a fraction of objects that are believed to be dormant or extinct cometary nuclei, objects with cometary origins that are no longer actively sublimating, but that retain the compositional and structural characteristics of cometary material. These objects are difficult to distinguish from primitive asteroidal objects in the near-Earth population based on spectroscopic observations alone, because the surface of a dormant cometary nucleus is covered by a lag deposit of refractory material that has the spectral appearance of a dark, carbon-rich asteroid, rather than the bright, icy surface of an active comet. The fraction of the near-Earth population that consists of dormant cometary nuclei is estimated at approximately 5 to 10%, based on dynamical models of the delivery of cometary material to near-Earth orbits, but the actual fraction is uncertain because the compositional identification of individual objects is ambiguous. If the potential parent body of the current fireball pattern is a dormant cometary nucleus, or a fragment thereof, its identification in the telescopic survey data would be challenging, because it would have the appearance of a dark, near-Earth asteroid rather than a comet. The search strategy for such an object would need to be based primarily on orbital properties, rather than on cometary appearance, requiring a search for objects on orbits consistent with the fireball trajectories among the known population of dark, near-Earth asteroids. The Jet Propulsion Laboratory's Small Body Database, which maintains the orbital and physical parameters of known near-Earth objects, would be the primary resource for such a search, and the WISE and NEO-WISE infrared survey data, which is particularly sensitive to dark objects that are difficult to detect in visible light, would provide the thermal emission measurements needed to constrain the sizes and albedos of candidate objects. The NEO-WISE mission, which operated from 2013 to 2024 as an extension of the Wide Field Infrared Survey Explorer, was the most effective survey for dark near-Earth objects conducted to date and characterized the sizes and albedos of hundreds of thousands of solar system objects based on their thermal infrared emission. The NEO-WISE data archive remains an important resource for the characterization of known near-Earth objects and for the search for potential parent bodies of newly identified debris streams. The analysis of the NEO-WISE data for candidate parent objects of the current fireball pattern is one component of the broader search effort being organized by the research teams engaged with the problem. The broader search effort illustrates a characteristic feature of modern meteor science, which is the integration of multiple datasets and multiple analysis techniques from what are nominally separate scientific disciplines. The identification of a new meteor stream or debris complex requires the combined expertise of atmospheric physicists who understand the physics of meteoroid ablation and fragmentation, dynamical astronomers who can calculate and compare orbital elements and perform integrations of orbital evolution, observational astronomers who can search the telescopic survey databases for candidate parent bodies, and mineralogists and geochemists who can interpret the spectroscopic and chemical data on the meteoroids in terms of their physical and compositional properties. The current research effort is drawing on all of these disciplines simultaneously, which is both its scientific strength and its organisational challenge. The organisational challenge of multidisciplinary research in planetary science has been addressed in part through the development of collaborative frameworks and data-sharing standards that allow researchers from different institutions and different countries to work together on shared problems without the friction that used to be associated with accessing and integrating data from different sources. The development of open data policies by major space agencies, the creation of shared databases like the Small Body Database and the Global Meteor Network Archive, and the use of collaborative platforms that allow real-time sharing of analysis results among geographically distributed research teams have all contributed to the acceleration of research on problems like the current fireball pattern. A pattern that would have taken years to analyse with the research infrastructure available 2 decades ago can now be characterised in weeks because the data is immediately available, the analysis tools are accessible, and the research community can coordinate efficiently across institutional and national boundaries. The accelerated pace of analysis made possible by modern research infrastructure means that the scientific community's response to the current pattern is faster than it would have been in previous eras. But it also means that the public communication of the science is occurring before the analysis is complete. The research teams are making preliminary findings public through conference presentations, preprint servers, and media communications before the peer-reviewed papers that will represent the definitive scientific assessment are available. This is appropriate given the potential significance of the pattern and the public interest it has generated, but it requires careful communication of the uncertainty associated with preliminary findings and the distinction between what is established and what is still being investigated. The media coverage of the fireball pattern has, in some instances, moved faster than the science, and has in some cases presented preliminary findings as more definitive than they are, or has connected the pattern to potential hazards that the current evidence does not support. The researchers working on the analysis are aware of this dynamic and are attempting to manage the communication of their findings in a way that is honest about uncertainty while being responsive to the legitimate public interest in the topic. The challenge of communicating scientific uncertainty to a public that tends to prefer definitive conclusions is one that the meteor science community, like many scientific communities studying natural hazard topics, faces routinely and has developed some experience in navigating. The history of previous fireball events that generated public attention and media coverage provides context for the current situation. The Chelyabinsk event of 2013 generated global media coverage and produced a period of heightened public interest in the near-Earth object impact hazard that the planetary defense community used productively to advocate for increased survey funding and for the development of planetary defense mission concepts. The 2016 fireball over Antarctica, detected by infrasound and radar but not visually observed, produced scientific interest but limited public attention because of its remote location. The 2018 Bering Sea fireball, which released energy equivalent to roughly 173 kilotons of TNT and was detected by the IMS Infrasound network but not widely reported publicly until months after the event, illustrated the gap between the scientific monitoring of large fireball events and the public awareness of them. The current pattern, occurring over the populated continental United States and detected by thousands of observers in addition to the instrumental network, has generated public attention that is proportional to its geographic visibility rather than necessarily to its scientific significance, which is still being assessed. The geographic visibility of the current pattern over the continental United States is relevant to the scientific analysis in a way that goes beyond the practical benefit of having a large population of potential observers providing reports to the American Meteor Society. The United States has the densest concentration of fireball monitoring infrastructure of any region on Earth, with the highest density of all sky camera stations, the best coverage by the NEXRAD weather radar network, and good access to the IMS Infrasound network. The detection efficiency for fireball events over the continental United States is therefore higher than for any other comparably sized region of the Earth's surface, which means that a given rate of fireball events over the United States will be documented more completely than the same rate over, for example, the Pacific Ocean or the Central Asian steppes. The concentration of the current pattern over the United States must therefore be interpreted in the context of the higher detection efficiency of this region, and the analysis must correct for this detection efficiency bias before drawing conclusions about whether the pattern is genuinely geographically concentrated or whether it appears concentrated simply because the detection is better there. The detection efficiency correction is one of the technically most demanding aspects of the statistical analysis of the current pattern, because it requires a model of the detection efficiency as a function of geographic location, time of day, weather conditions, and event characteristics that is more detailed than what has been routinely applied in previous analyses of the sporadic fireball background. The development of this correction model is one of the current active areas of the analysis effort, drawing on the instrumental performance characteristics of each component of the detection network and on the historical record of detected events that can be used to calibrate the model empirically. Getting the efficiency correction right is essential for the scientific validity of the pattern claim, because an incorrectly estimated efficiency could either create the appearance of a pattern in genuinely random data or obscure a real pattern by attributing the excess of detections to detection efficiency rather than to a genuine excess of events. The night sky above the geographic corridor of the current pattern has been watched more carefully in the weeks since the 3 initiating events than it normally is, both by the instrumental network and by the community of amateur astronomers and meteor observers who have been following the story and who have deployed their own cameras and observing resources to monitor the region. The amateur astronomy community in the United States is a significant scientific resource for meteor science, providing both the observing effort and the cultural enthusiasm for the subject that professional networks alone cannot supply. The American Meteor Society's network of trained observers, the video meteor observation groups that operate independently of the professional networks, and the individual amateur astronomers who point cameras at the sky on clear nights, all contribute to the overall monitoring capability in ways that are valued by the professional research community. The collaboration between professional and amateur astronomers in meteor science is one of the most productive examples of citizen science in any field of natural science, and the current fireball pattern has energized the amateur community in a way that is increasing the effective coverage of the monitoring network over the affected region. Additional camera deployments, extended observing sessions on clear nights, and the systematic reporting of observations through the American Meteor Society's reporting system are all contributing to the data accumulation that will ultimately resolve the question of whether the current pattern is real. The scientific analysis of the amateur data requires the same rigor as the analysis of the professional network data, including careful quality assessment of individual observations and appropriate weighting of events detected by cameras with different sensitivity thresholds and field of view characteristics. But the volume of additional data being generated by the energized amateur community is a genuine scientific resource that the professional research teams are actively working to incorporate into their analysis. The resolution of the question of whether the current fireball pattern is real, and if so, what is causing it, will come from the data. It always does. The scientific method applied to the observation of the natural world requires that conclusions follow from the evidence rather than precede it, and the evidence in this case is still being collected and analysed. The researchers working on the problem are following the method carefully and rigorously, aware of the public attention that the pattern has generated and committed to providing a scientifically defensible answer rather than a premature one. The answer will be published in the peer-reviewed literature, where it will be scrutinised by the broader scientific community, refined in subsequent studies, and eventually integrated into the ongoing understanding of the near-Earth object environment that the monitoring network is continuously building. In the meantime, the fireballs continue to occur. Every night, across the continental United States and across the rest of the Earth's surface, the planet sweeps through the debris of the solar system, and that debris burns in the upper atmosphere in the brief, brilliant events that humans have watched and wondered about since the first eyes looked upward at the night sky. The rate of these events is high enough that any sufficiently attentive observer who watches the sky for long enough will see one. The three events that initiated the current scientific attention were seen by tens of thousands of people across the western and central United States, captured by hundreds of cameras, recorded by infrasound stations thousands of kilometers away, and are now being analysed by research teams who are trying to determine whether they represent something that was already there in the near-Earth object environment or something new that the environment has recently produced. The near-Earth object environment is not static. It changes as objects are delivered from the main belt, as comets evolve and fragment, as planetary encounters scatter objects onto new orbits, as YORP and Yarkovsky effects slowly modify the orbital and rotational states of individual objects over geological time. The Earth samples this changing environment through its continuous passage through interplanetary space, and the Fireball record is the most sensitive probe of that sampling, at the small end of the size distribution where telescopic surveys cannot reach. The current pattern, whatever its explanation, is a new entry in that record, a new data point in the ongoing characterization of the environment that surrounds the planet, and that delivers, with a frequency and at a size distribution that the monitoring network is progressively better at characterizing, the material that burns in the night sky and occasionally reaches the surface as the meteorites that preserve in their minerals and isotopes the oldest and most pristine record of the solar system's formation. The connection between the fireballs burning overhead and the solar system's 4.5 billion year history is one of the things that makes meteor science compelling beyond its immediate practical relevance to planetary defense. The material entering the atmosphere as a fireball has been travelling through interplanetary space since it was last part of a larger body, which may have been billions of years ago. The minerals in a recovered meteorite from a large fireball event carry the isotopic signatures of the nuclear processes that produce the elements they contain, the supernovae and other stellar events that scattered those elements through the interstellar medium before they were incorporated into the solar nebula from which the Sun and planets formed. The fireball that burns for a second in the night sky is, in this sense, a visitor from the deep past of the solar system, a sample of the material that was present at the beginning and that has been preserved in space, unchanged by the geological processes that have transformed the Earth's surface for billions of years. The three fireballs that initiated the current scientific attention were, each of them, objects that had existed in interplanetary space for some period of time before their encounter with the Earth's atmosphere ended their independent existence. Whether they were fragments of a single parent body that fragmented recently, or samples of the general sporadic background that happened to have arrived in a statistically unusual cluster, or something else that the ongoing analysis will reveal, they carried with them information about where they came from and what they were made of that the instruments recorded as they burned. That information is now in the archive, being analysed, contributing to the understanding of the near-Earth object environment and of the solar system history preserved in the debris that fills interplanetary space. The fireballs are gone, the data remains, the analysis continues. The sky above the corridor of the American continent that the pattern has traced is being watched more carefully than usual, and every clear night adds new observations to the record that will eventually resolve the question of what the pattern means and why the experts who study it went quiet when they first saw it in the data. The watching continues, the data accumulates. The solar system delivers what it delivers, indifferent to the instruments that record it and the researchers who analyse the records, continuing the slow dynamic evolution that has been underway since the disk of gas and dust that surrounded the young sun began to coalesce into the planets and smaller bodies that constitute the solar system today. The Earth moves through that system at 30 kilometers per second, sweeping up debris at a rate determined by its cross-sectional area and the local density of interplanetary material, recording each encounter in the Fireball archive that the monitoring network maintains. The archive is a running record of the solar system's delivery to the Earth's doorstep, and every so often, it contains something that looks different from the background in a way that requires explanation. The current pattern is one of those somethings. The explanation is being worked on, the sky is being watched, the data is being collected, and the answer, when it comes, will be in the numbers. The numbers tell stories that the human eye cannot read directly. A fireball visible from the ground for 3 seconds contains, in the data stream flowing from the instruments that recorded it, information about the mass, velocity, composition, trajectory, fragmentation behavior, and pre-atmospheric orbit of the object that produced it. Extracting that information requires mathematical tools developed over decades of meteor science research and computational resources that have only become widely available in the past generation. The science of reading fireballs is young in the sense that the tools required to do it well have not been available for long, and the accumulation of the expertise required to apply those tools to the full complexity of the problem is still ongoing. The velocity measurement is the single most important quantity for characterizing a fireball and for calculating its pre-atmospheric orbit, because the velocity at atmospheric entry determines both the kinetic energy of the event and, when combined with the trajectory direction, the heliocentric orbit from which the object arrived. The velocity of a meteoroid entering the Earth's atmosphere can range from approximately 11 kilometers per second, the minimum set by the Earth's escape velocity for objects that were essentially at rest relative to the Earth before entry, to approximately 72 kilometers per second, the maximum for a head-on encounter with an object moving at the maximum speed consistent with a bound solar orbit in the opposite direction to the Earth's motion. The velocity distribution of the sporadic fireball background peaks at intermediate values around 15 to 25 kilometers per second, reflecting the orbital velocity distribution of the near-Earth object population from which the sporadic meteors are drawn. The 3 events in the current pattern have entry velocities that have been estimated from the camera data using the standard technique of measuring the angular velocity of the fireball across the field of view of cameras at known locations and converting the angular velocity to a linear velocity using the triangulated trajectory geometry. The velocity estimates from this analysis carry uncertainties that reflect both the measurement uncertainties in the angular velocity determination and the sensitivity of the orbital calculation to small errors in the velocity at the level of precision achievable with the current camera data. The velocities estimated for the 3 events are in the range of 18 to 22 kilometers per second, consistent with the sporadic background, but not diagnostic of any specific orbital population. Velocities in this range are consistent with both asteroidal and cometary orbits, because the overlap between the velocity distributions of these 2 populations at intermediate velocities is substantial. The velocity information is necessary but not sufficient to identify the population of origin for the current events. The deceleration of the fireball during atmospheric traversal provides additional information about the mass and bulk density of the incoming object that complements the entry velocity estimate. A meteoroid entering the atmosphere decelerates as it transfers momentum to the atmospheric gas molecules it collides with. The rate of deceleration depends on the ballistic coefficient of the object, which is the ratio of its mass to its cross-sectional area times its drag coefficient, and on the atmospheric density along its path. A high-density compact object has a high ballistic coefficient and decelerates slowly, penetrating deep into the atmosphere before depositing most of its energy. A low-density porous object has a low ballistic coefficient and decelerates rapidly, depositing most of its energy at high altitude. The terminal altitudes of 38 to 42 kilometers observed in the current pattern are consistent with objects of low ballistic coefficient, which is itself consistent with the low bulk density expected for either cometary debris or for highly porous carbonaceous asteroidal material. The combination of entry velocity, deceleration profile, and terminal altitude for the 3 current events is being used in a coupled analysis that attempts to simultaneously constrain the bulk density and tensile strength of the incoming objects, using models of meteoroid ablation and fragmentation that have been calibrated against events for which post-event ground truth, in the form of recovered meteorite fragments with measured physical properties, is available. This kind of constrained inversion of the fireball data to extract physical properties of the incoming object is one of the most technically demanding aspects of meteor science, and one where the results are most sensitive to the assumptions built into the ablation and fragmentation models. Different models, using different assumptions about the physics of the fragmentation process, can produce significantly different estimates of the physical properties for the same observed fireball light curve and deceleration profile. The development of models that are adequately validated against ground truth data is an ongoing research priority in the meteor science community. The ground truth for fireball physical property models comes primarily from two sources. The first is the recovered meteorite samples from fireballs, for which the pre-atmospheric orbit is known from camera and radar observations, and for which sufficient material survived to the surface to allow laboratory analysis of the physical and compositional properties. The number of meteorites with known pre-atmospheric orbits is small, currently around 40 worldwide, because the conditions required for both instrumental detection of the fireball and recovery of meteorite material are jointly satisfied in a relatively small fraction of cases. Meteorite recovery requires that the object survive to the surface in sufficiently large fragments, which favours strong stony or metallic objects, while the most scientifically interesting material, in terms of characterising the compositional diversity of the near-Earth object population, includes many fragile objects that are completely ablated before reaching the surface. The bias towards strong objects in the meteorite collection means that the ground truth calibration for fragile object ablation models is particularly poor and relies heavily on extrapolation from the properties of stronger objects. The second source of ground truth for fireball physical property models is the direct observation of meteoroid fragmentation in the upper atmosphere using high-resolution imaging systems. Several research groups have developed camera systems capable of resolving the individual fragments produced during the catastrophic fragmentation of a meteoroid in the atmosphere, providing direct observational evidence of the fragmentation process that can be compared with model predictions. The high spatial and temporal resolution required for this kind of observation limits the field of view of the cameras and therefore the fraction of fireball events that can be captured with the necessary resolution. Events that happen to occur in the field of view of a high-resolution imaging system provide particularly valuable scientific data, and the deployment of additional high-resolution cameras in the geographic corridor of the current pattern is one of the responses to the pattern that the research community is organising. The radar observation of fireballs provides a different kind of data from the optical camera observations and is sensitive to aspects of the atmospheric interaction that optical observations cannot access. When a meteoroid ablates in the upper atmosphere, it leaves behind a trail of ionized gas along its path, the meteor trail, that reflects radio waves with an efficiency that depends on the electron line density in the trail. The echo duration and range rate measured by meteor radar provide information about the height, velocity, and deceleration of the meteoroid that complements the optical data. The all-sky interferometric radar systems operated by several research groups provide continuous monitoring of the meteor flux and are particularly sensitive to smaller meteoroids that do not produce optically visible events. The CMOR, the Canadian Meteor Orbit Radar, operated by the University of Western Ontario, and the SAMA, the Southern Argentina Agile Meteor Radar, together with a network of similar systems in Europe and Australia, provide near-continuous radar monitoring of the meteor flux, with the ability to determine individual meteor orbits from the measured velocities and directions of the radar echoes. The radar systems detect meteors across a size range extending below the threshold of optical visibility and provide a statistical characterization of the meteor flux and its directional distribution that is less biased toward bright events than the optical fireball networks. The radar data from the period of the current fireball pattern is being analysed for evidence of elevated sporadic activity or directional anomalies that would corroborate the pattern identified in the optical and infrasound data. The directional analysis of the radar data is sensitive to changes in the sporadic radiant distribution, the distribution of directions from which meteors are arriving, that might indicate an excess from the direction associated with the current fireball pattern. The sporadic radiant distribution has a known large-scale structure, with several broad radiant concentrations corresponding to the major sporadic sources identified by decades of radar observation. These sporadic sources, which include the helion and anti-helion sources associated with debris from the inner solar system, the north and south apex sources associated with material on high-inclination orbits, and the toroidal sources associated with debris from short-period comets, contribute to the background against which any new stream or concentration must be identified. The statistical identification of a new excess direction in the sporadic radiant distribution requires careful comparison with the known source structure and appropriate statistical testing against the hypothesis of no excess. The analysis of radar data for new sporadic source detection has a long history in meteor science and has led to the identification of numerous minor meteor streams that are too weak to be visually apparent, but that are statistically significant in the radar data. The techniques used for this analysis, including wavelet transforms and other pattern recognition methods applied to the multidimensional distribution of meteor orbits in the radar data, have become increasingly sophisticated over the years and are capable of detecting new streams at significance levels that were not achievable with the analysis methods available to earlier generations of researchers. The application of these techniques to the current radar data from the period of the fireball pattern is one component of the comprehensive analysis effort and will provide an independent assessment of whether the optical and infrasound pattern is corroborated by the radar data. The question of what the pattern means for the people living under the corridor it traces across the American continent is one that requires careful calibration of scale and probability. The fireballs that produce the pattern, objects in the half-meter to meter size range, are not individually hazardous to people on the ground in any meaningful sense. Objects of this size are completely ablated in the atmosphere before reaching the surface under the entry conditions that the current events represent, and the energy they release is deposited at altitudes of 38 to 42 kilometers, far above the altitude at which a pressure wave from their fragmentation would be felt at the surface as anything more than a distant sound. The individual events are spectacular visual phenomena that many people in the affected corridor have been fortunate to witness, but they are not dangers in any operational sense. The hazard relevance of the pattern, to the extent that it has hazard relevance, is indirect and statistical. If the pattern reflects the Earth's passage through a debris concentration that follows a size-frequency distribution consistent with having been produced by a specific fragmentation event, then the concentration likely contains objects larger than those that have been detected, and those larger objects may eventually encounter the Earth on their own orbital trajectories. The probability and timing of such encounters cannot be calculated from the current data, because the larger objects in the hypothetical concentration have not been directly detected and their orbits are not known. What can be said is that if the fragmentation hypothesis is correct, and if the debris concentration includes objects in the 10 to 100 meter size range at the frequency predicted by the extrapolation of the detected size-frequency distribution, then the Earth is moving through a region of interplanetary space with an elevated local density of potentially hazardous objects that are too small to be detected by current survey programs. This is the consideration that has the planetary defense community paying attention to the current pattern. Not because any specific object in the pattern has been identified as threatening, not because the current events represent a danger to people on the ground, but because the pattern, if real, is telling the community something about the local near-Earth object environment that the survey programs are not able to tell them, something about the density and distribution of objects at a size scale that is currently below the detection threshold, and something about the processes that are generating new debris in the near-Earth environment through the fragmentation of larger bodies. Understanding these processes is essential for developing the probabilistic models of the impact hazard that inform the planning of planetary defense capabilities. The planetary defense planning process is fundamentally a probabilistic exercise. It involves estimating the probability of an impact of a given size within a given time frame, comparing that probability against the consequences of the impact to calculate the expected harm, and then evaluating the cost-effectiveness of different mitigation options. The probabilities involved span an enormous range, from the essentially certain probability of a 1 meter object striking the Earth somewhere on its surface within the next year, to the extremely low but non-zero probability of a civilization-ending impact from an object larger than 10 kilometers within the next million years. The planning is not about eliminating the risk, which is impossible, but about reducing it to levels that are appropriate given the available resources and the competing demands on those resources. The current fireball pattern, if it is real, is a data point that modifies the probability estimates in the middle part of the size distribution, in the range between the sub-meter objects that produce fireballs too small to be directly hazardous, and the 100-meter objects that produce Tunguska-class impacts capable of causing regional damage. This is the part of the size distribution that is most poorly characterized by existing data, because the objects are too small to be reliably detected telescopically before Earth encounter, and too rare to be well sampled by the fireball network over the short period of its operation. A pattern that suggests the local density of objects in this size range is elevated above the background statistical expectation, is therefore a potentially significant input to the probability estimates, even if the elevation is temporary and specific to the current orbital neighbourhood of the Earth. The sky above the corridor has been watched every clear night since the 3 events that started all of this. The cameras have been running. The infrasound arrays have been listening. The radar has been sweeping the upper atmosphere on its normal schedule, indifferent to the extra scrutiny that the research community has been applying to its data. The archive has been growing, one night at a time, adding observations that will either strengthen the case for the pattern or quietly dissolve it into the statistical background where coincidences live. The people who live under that corridor have mostly gone back to their lives. The brief period of public attention that followed the reports of 3 brilliant fireballs in 11 days over the western and central United States has faded the way public attention to natural phenomena always fades, replaced by the next thing that demanded it. The sky looks the same as it always did. The night is dark and the stars are there, and occasionally something burns across it for a second or two and is gone, the way things from space have always burned and gone, since long before anyone was watching. The watching is relatively new. The instruments that captured the 3 events, that measured their velocities and terminal altitudes, and infrasound signatures and pre-atmospheric orbits, have only been in place for a fraction of the time that the solar system has been delivering material to the Earth's atmosphere. The fireball archive that the global camera network is building began accumulating in earnest only in the past decade. 3 decades of systematic seismic monitoring, a century of infrasound records. These are thin slices of time laid against the 4.5 billion years that the Earth has been sweeping through the debris of the solar system at 30 kilometers per second. The pattern, if it is real, has probably repeated before. The Earth has probably passed through this debris concentration, or one like it, at some point in the geological past, and the fireballs it produced burned in a sky that no instrument was watching and left no record except the faint chemical signature that might be preserved in some layer of sediment somewhere that no one has yet thought to look for it. The 3 fireballs that did leave a record left it in the archive. The data is there, the analysis is ongoing. The researchers who went quiet when the numbers first arrived are working, carefully and without the urgency that the public attention imposed on the story, toward an answer that the evidence will either support or it will not. Science does not hurry for audiences. It moves at the pace the problem requires. What the problem requires, in this case, is more data, more clear nights over the corridor, more events, if they come, that can be added to the statistical sample, more time for the dynamical analysis of the orbital similarities to be completed with the rigour that a confident identification demands, more coordination between the optical and radar and infrasound networks to build the complete picture of the atmospheric interaction that each dataset partially captures, more time for the search of the telescopic survey databases to find, or not find, a parent object whose orbit connects to the fireball trajectories in a way that explains the pattern. The more data will come, it always does. The sky keeps producing events, and the instruments keep recording them, and the archive keeps growing, and eventually the question of whether the current pattern is real resolves into either a confirmed discovery or a confirmed coincidence. Either outcome is scientifically useful. A confirmed discovery adds to the understanding of the near-Earth object environment and of the fragmentation processes that populate it with debris. A confirmed coincidence adds to the understanding of how to distinguish signal from noise in a dataset that is inherently noisy and where the human tendency to find patterns can mislead even careful researchers. The solar system is large and old and full of material that it delivers to the inner planets on timescales ranging from the continuous to the catastrophic. The Earth intercepts some of that material every day, burning it in the upper atmosphere in events that range from the invisible to the spectacular. The 3 spectacular events that started this story burned for seconds each, releasing their energy at altitudes too high to affect anyone on the ground, and then were gone. What they left behind was light captured by cameras, pressure waves recorded by microphones, ionization detected by radar, and a question written in the numbers that the instruments produced. The question is still being answered, The instruments are still running, the archive is still growing. And the solar system, which has been asking questions like this one for 4.5 billion years without waiting for answers, continues its slow delivery of material to the third planet's doorstep, one fireball at a time, one clear night at a time, patient as physics, indifferent as gravity, and entirely unaware that anyone down here is watching.